Okay, so it's going to be Unit 8, Worksheet 5, our energy transfer and power calculations. We're going to start with problem number 2. Jill pulls on a rope to lift a 12-kilogram pail out of a well, while the clumsy Jack watches. For a 10-meter segment of the lift, she lifts the bucket straight up at a constant speed. How much power is required to complete this task in 5 seconds? Complete the energy bar graph as part of your solution. Well, when it comes to this, a lot of times when we're setting up these energy bar charts, we like to use a diagram to try and make sense of the scenario. This problem doesn't have one, so we're going to create one. We have Jill pulling on a rope to lift a pail out of a well, and this is going to be for a segment of the lift. So it's probably safe to assume that for segment A, this thing is already out of that water, and it's being lifted up by a rope. We know that this is going to be a 12-kilogram pail, so my mass is 12 kg. It's going to be a 10-meter segment of the lift. So I can probably define this starting point at A as a height of 0. And then we know that it is currently moving, so I'm going to be adding a velocity vector here. I'm going to say position B is just going to be when the pail is even higher up. It's still going to be moving up, so we still have that velocity vector. It still has the same mass, but now that it is 10 meters up, the height can now be 10 meters for that 10-meter segment of the lift. Oh, and it says constant speed. So I can say that this velocity is the same as that velocity. Now, this is probably going to be good enough to set up our LOL chart. The first thing that we're going to do with this energy bar chart is to identify the system. Now, I'm going to definitely be looking at the pail, because that's what I've included in my problem. Probably going to be including the rope, because I can see that, and probably the Earth, because we're talking about the Earth's gravitational field. I decided not to include Jill in my diagram, because, well, it's just a bit hard to include her in the well. So I'm going to put Jill outside of our system. Now that we've set up our system, I'm just going to be focusing on the pail, the rope, and the Earth. At position A, it is moving, so I should probably have some bars of energy represented in the kinetic energy account. I'm going to go with my old standby of 2. 2 is a great number to start off with. Oh, but one thing I know is this is a constant speed. So position B should have the same amount of energy stored in its kinetic account. I'm going to put 2 bars there as well, 2 whole bars. Now for my gravitational. Position A, we define that as our 0 reference level of 0 meters. So I'm going to say we have 0 amount of energy represented in gravity at position A. And then position B, we've moved up. So I'm going to be adding 2 bars of energy right there. Now when it comes to our elastic, I tend to think of elastic as more like rubber or things that can really stretch easily. Probably not like an old style rope that you might associate with a well. So I'm going to give it 0 bars of elastic before and after. However, if we're talking about like a fancy modern rope that can stretch a little bit before it breaks, we can add some elastic energy there. But the amount of energy associated with the elasticity would be the same in both accounts because, well, it's going to be proportional to the amount of force that is acting on that bucket, and that rope should be tight, so the amount of elastic energy would be constant in both. Now, I typically don't start off with thermal, so position A isn't going to have any. Thermal is typically associated with friction, and that's going to be when like 2 things rub against each other. Because this bucket is being lifted straight up, it's not rubbing against anything, so I'm going to assume there's no thermal here. After I've set up both of those bar charts, the left one and the right one, I'm going to see if they're balanced. Well, they're not. I have 2 bars of kinetic at position A, and that's it. I have 2 bars of kinetic and 2 bars of gravitational at B. I want to see if I can adjust either position A or position B's quantity in order to make them balanced. Well, I can't really change the amount of EK at both A and B because those have to be proportional. They have to be the same amount as each other because it's a constant speed. I know I don't have any EG at position A because that was our, well, relative height of 0. And for position B, I know I'm above that, so I have to have more EG. So I can't balance it just by looking at those bar charts. So that means that there has to be energy entering our system. This is going to be entering from Jill pulling on the rope. She is working on our system. So this qualitative energy conservation equation, I have the amount of kinetic energy at the beginning is equal to the amount of kinetic energy at the end plus our gravitational energy. And because Jill was working on this system, she was transferring energy into it. So she was adding that over at the beginning. One thing that I can also say is because I have the same amount of energy associated with motion, I can actually probably cancel these out. So really my equation can just be working is equal to my amount of gravitational energy that I've gained by the end of this problem. So when we're trying to quantify how much power is required, we need to look at our change in energy, or the amount of work that was done on the system over the time. Well, we're told the time is 5 seconds, so we know that. We just need to quantify our working. Well, our working is going to be equal to our equation for our EG, mgh. We know this is a 12 kilogram pail. We know that our G is 9.8 newtons per kilogram, and we know that this is going to have an H, or that's change in position, of 10 meters. So when I plug this into a calculator, I will do 12 times 9.8 times 10, and I will end up with the amount of work, or the energy that is transferred into this system, as 1,176 joules of energy. So I'm going to take that amount and actually plug it into this equation up here. So that's 1176 joules of energy that were transferred into the system in 5 seconds. So I'll divide that 1,176 joules by the 5 seconds, and I will end up transferring in 235.2 joules of energy every second, or we can say that that is going to be watts. This right here is going to be our answer. The amount of power required to complete that task in 5 seconds is 235.2 watts.